but let's go ahead and get started. So we're gonna pick off where we left off last time. We're gonna look at our wages data sets. Okay, so this was where we were looking at a couple examples of dummy variables and categorical variables, right? And so we start to get a little bit trickier in the way that we interpret things when we have dummy variables, because they're interpreted in a slightly different way than with our continuous variables. So last time, right, we had generated this model. Where we included education, age, and sex. And we run this. Oop. Gotta load the data. Oh, hang on. What's going on? I don't have wages in here. Oh. There we go. Okay, so as a quick refresher, right, the way in which we interpret our continuous variables is the same, every year of education increases your earnings on average by $44.70 per year of education, and per year of age by $280. And then where it starts to get a little bit funky, right, is we assume that the intercept is kind of the base level. And in this case, our base level for our dummy variable is female. Here we have male. If you are male, you would increase the intercept up by $21,000, right? And so males on average make $21,000 more than females. Okay. Any questions about any of this? Hopefully this is all still ringing a bell as we review this. And then I believe, let's see, the last thing we looked at was this interaction model. And I'll just kind of quickly review this one as well, just to make sure our interpretation is straight. And if you're confused about this, please don't hesitate to let us know. Right, so interaction, we're now interacting education and gender. So we have an additional variable here. And we can see how this changes the model, right? And so we have a baseline of negative 39,000. And then education, you're essentially treating as like a baseline slope, where we say both males and females, or to be less confusing, everyone makes $38.50 more per year of education, but we also have this interaction term of education and female, education and male. And so in addition to that $38.50, males also on average make $15.44 more per year of education. Okay? So the actual slope of that education variable is now different between males and females. And the way you could think of it holistically for male is adding that $38.50 plus the $15.44. Okay? Any questions about this? Yeah, so data analysis is also a great way to like empirically demonstrate things like gender inequities. This is like a slightly older data, but I would probably venture to guess that gap still exists to some extent. Okay, so going back actually to the first model that we ran, as we look at the results here, what do you guys think about this model in general? Anyone willing to speak up about, anything that we've covered before? If we're thinking about, I don't know, like the quality of a model. Anyone? Good model, bad model, okay model, and how do you know? Yeah.
Although all the predictors or coefficients are significant,
Okay.
the R squared is kind of low.
Okay. So let's be more specific. What do the coefficients being significant tell us?
There's a relationship.
Yeah, right. So, okay, maybe we believe that there are relationships being described by the data, and the R squared, what is that telling us?
How good is or I'm gonna say line, but it's not a line, right?
Sure, yeah.
How good this line is going through all of our points.
Yeah, how much of the variability is explained by that not so line, hyperplane, whatever we'll call it, right? Yes. Yeah, that's right. So I'm not going to say anything specifically about how good or bad the model is, but what I'm going to say is, well, it seems like our variables are probably explaining portions of the relationship between earnings, right? And so if I really cared about understanding specific relationships, maybe this model is actually doing a decent job because I'm getting statistically significant variables. However, if I were to think about maybe predicting outcomes, there's probably a lot of variation that isn't explained in the model that may lead to imprecise predictions, for example. Right, and so I'm trying to get us to be a little bit more precise about the ways in which we're judging aspects of the model. What other things have I asked us to look at when it comes to judging how good or bad a model is? One other, yeah.
I remember you mentioning about the significant codes, like the asterisks on the.
Yeah. So that's what he was mentioning about how the variables are significant. So this is indicating that likely there is a real relationship between the variables and our outcome variable of earnings. That is to say, I would be hard pressed to think that your level of education wasn't related to your earnings. That's what the significance tells us, right? But then the caveat is just because we know that that's true doesn't mean that our model is actually telling us in a very precise way what your earnings are, and we can kind of get a sense of that from this, right? What about if our model is biased or not? Do any of these tell us anything about that? What was an easy way for us to determine model bias? Or what does it mean for a model to be biased? I don't know if I've actually talked about this formally, but if someone wants to take a stab at it. Right, so if we are, oh yes, go ahead.
Okay, because you said how we could check
Yes, yeah.
I think we said with residual plots.
Yeah, great. And so with residual plots, what are we looking for and what might indicate bias?
So you're looking for, I think, a random distribution, right? Around 0.
Around 0, that's right. So let's do that. So our residual plot, right, the x-axis is y hat and the y-axis is the residuals. So I'm going to plot our y hat, which is thus the predict of our wage model. And we're going to plot that against our residuals of the wage model. Okay. And we'll blow this up. All right. What do you guys think? Yay or nay? I see thumbs down. Yeah, so we got this little weird thing happening. It looks like there's some kind of straight line cutoff that happens. Any other features of this? So yeah, this we've got some weird thing happening here where you've got the straight line. Anything else notable about the residuals that you guys see here? Huh?
The spread of residuals equals wage.
Okay. So the spread, yeah. So like here, it doesn't look like there's very much distribution. There's not much variation. Over here, there's more variation. And over here, there's a lot of variation. Yep. Okay. And so that actually, that is a feature that you may actually see pretty commonly. We call that heteroskedasticity, where the error term is like correlated with your outcome in some way. That's not like a total deal breaker, and there's actually some ways of dealing with that where you change your standard errors to reflect the fact that you have these larger errors. But yeah, it's an important feature to notice. But probably the more important one is this kind of cutoff thing that you're seeing here. One common thing that can happen is for variables that have like cutoffs in their values, right? And so we think of in our y variable, you typically would want that to be continuous, right? Are earnings continuous? What do you guys think? You're nodding. So I would say earnings are likely continuous, except there is a weird thing about the earnings, which is that can I make $10,000 a year? Can I make $50,000 a year, right? $100,000 a year? Can I make negative $10,000 a year? Well, okay, I guess technically you could, but not in this data. So they only look at the positive incomes, right? And so actually one of the common ways that you deal with this like one-sidedness is actually transformation, which we've talked about before. Yeah, I'll just do it below. So you can actually take the log of the variable that you want to get rid of anything worth zeros and below. And that will create a distribution with a long tail on one side, but not on the other tail. So it better reflects the kind of spread of the data that you want in your model. And so this time, the interpretations are now changing a little bit. Remember, now for a unit change in a particular variable now results in what kind of change in our outcome? Who remembers from last time when we were talking about the log transformations? So this is a log level. So if I increase my education by 1 year, how much do my earnings change? 16%, yep. And if I increase my age by a year, then my earnings go up by about 0.9%. And if I'm a male, then I make 100% more than female, or double. Okay? And let's plot this really quick. Oh. And see, have we totally fixed this? So some of the stuff has gone away and the spread is a lot better, but you still have this line of stuff. Okay. And so one of the things you want to do is to try and identify, what's so special about these points that are happening here, and showing up in the residuals in like a very clearly patterned way, right? This is not like a random looking event. And to reflect more broadly, when you're doing your analysis, this is the type of thing that you would want to be thinking about and looking at and trying to fix, right? So not just looking at your standard errors and your R squared, we want to think about bias and how it pertains to residuals. We want to see what's happening and see if we can deal with this. So without going into too much detail, what I can tell you is that actually, if you look at the data, what's happening is you have people who are doing regular jobs and earning, regular salaries, right? And there's variation in those salaries, but then there's a small group of people who are earning very small amounts of income. And so these might be, like temporary jobs, like babysitting or something like that, where it's clearly not like an annualized salary. And that is, those are essentially outliers in the model. And so in this case, one of the things, if I wanted to fix the residuals, is let's just see what happens if I get rid of those. So I've set it up exactly as I've typed before, but now in the data, I'm only going to include people who earn more than $1,500 a year. And that is meant to sort of explicitly get rid of those kind of corner cases that I was just talking about. So if I run this, you can see now my residuals are fixed, right? I have essentially a random set of residuals that are generally kind of centered around 0. This is the type of residual plot that you would want to see that indicates that your model is not biased in some way. So in your repertoire of checks, I would strongly recommend that looking at the residual plots is one of the sort of more important things that you could include in your analyses. Okay. And the degree to which that affects the results, right? It changes some of these numbers a little bit. Actually, notably here, right, it's 44% higher instead of 100% higher. And then, the other coefficients get slightly affected. Okay, any questions? No? All right.
Could you
Oh,
show
yeah.
the line where you plotted it, the wages?
Oh, yeah.
That.
Sorry, here you go. Yeah, it should be the same as the previous one. All right. So that tidies up discussion from last time. And now we will, move on to lecture 6. So I've showed this kind of example a couple times now where we've got this set of data and we draw a line through it. And I've talked about this idea that we can create other types of fits that go through this data, right? So we've seen this idea where I could do something like this. And the concept of giving a fit line more flexibility, we can kind of essentially think of you're providing more degrees of freedom, and you're essentially creating a more complex model to allow for a better fit, right? So we can create a better fit by adding more explanatory variables. And so essentially what we're doing is changing the functional form. So like one way we could do this is by, for example, adding like more exponentiated variables, right? So we could do, y equals beta 1x plus beta 2x squared plus beta 3x cubed plus ... beta n x n. Okay. So we've talked about in this particular example, if I were adding more points, however the original data set was generated, we consider that kind of the data generating function. We add more points from that function that looks something like this, and all of a sudden, the blue model might suddenly look a lot worse. Okay? So, how do we think about this trade-off between how much I go from red to blue, the red line to the blue line, to better predict points versus going too far and like overfitting the model, right? So maybe there's something in between the red line and the blue line that I'm trying to get to, to give me the sort of best model outcomes possible. And this trade-off is kind of a fundamental, inescapable part of doing these types of estimations. And this is known as the bias variance trade-off. And this is the fundamental concept that we're going to revisit again and again as we go through different models in this particular class. Okay, so this is the whole thing where you have, okay, so low variance, high variance, low bias, high bias. Yeah, to demonstrate this kind of qualitatively, that was a bad circle. Suppose we have our targets here. Okay, if you have low bias and low variance, then you are consistently getting kind of the right answer. You could have low bias but high variance, in which case you have a higher spread about the right answer. You could have high bias but low variance, where you are consistently getting the wrong answer, and you can have high bias and high variance, where you are both getting the wrong answer and you have a large kind of spread. Okay. So the idea is when you have less complex models, you may tend to have higher levels of bias. But then when you increase the complexity of your model, you may actually increase in your variance. So let me write out equation here. So error of x, so this is equal to something like this, the expected value of y minus y hat squared. And we can separate this out. So you don't need to memorize this part of it. But they would derive this for you in a stats class. Okay, expected value predicted minus expected value of f hat x squared. Oh, should be here. Okay. And so actually the point of me writing this out isn't necessarily to understand the root math behind this, but that actually there are three main components to an error term. Okay. And those three pieces are bias plus variance plus noise. So I don't know why this thing showed up. Hang on. There we go. Okay. Bias, variance, and noise. These are the three components of our error term. The noise is kind of inescapable. That's kind of like the random error part that you can't really get rid of. And then the bias and variance really depend on your model choice. So what this ends up looking like is something like this. So if this is our error, we can look at model complexity here. And so as I was mentioning, the bias term decreases as our model complexity goes up, right? We are better able to fit through our data points. So bias ends up looking something like this. Variance, on the other hand, increases as you increase in model complexity. And I'll show an example of this in just a second. And then our total error looks something like this. And so this is variance plus bias. So the idea is maybe the linear model is more on the left-hand side, and my super squiggly model is more on the right-hand side. And what you're really aiming for at the end of the day is here. This is the goal for finding the appropriate model that decreases our error term as much as possible without overfitting, but complex enough that we're reducing our bias to the greatest extent possible. Okay? Yeah?
Is the definition of bias equivalent to the residual?
No. The residual is your overall error term, so that would be the why is this not working? Okay, oh, here we go. That's kind of like the error is kind of like the expected value of your residual. The bias is the difference in the expectation of the actual predicted value with your any given value. Let's see. Would that be the same thing as the residual? Not. So I think it'll look very similar to the residuals, but there might be some cases in which you could actually be a little bit different because of differences between the expectation and the actual predicted value. Yeah. But what this ends up looking like practically, right? So if we were thinking about attributing the portion of the residual bias to, or the residual error to bias or variance, right? You know, if I had something like this, this is like bias error stemming from the improper model fit to the data. That's different from, right, the idea that I have like some kind of function here where in the true data generating function that my data is like overfit in some way. And so this would be like variance error. Okay. So the whole point of what we're trying to do is to identify the sweet spot between these. Yeah.
One question. I would have expected bias and variance to be the other way around. So if, when model complexity increases, I would have thought the bias would increase too because you are overfit, or you run the risk of overfitting. And I would expect the variance to drop because you are getting closer to the data. Why is that wrong?
So think of it this way. Bias, yeah, we need to be precise about the definition of the way we think about bias. Bias is where you are consistently getting wrong answers, right? So in the example on the right-hand side, we are the bias is essentially eliminated because you are almost like you're centering, your fit line is almost kind of getting predictions wrong equally on both sides, right? And the more complex you get, right, that can actually increase the variance error portion because you're like getting farther and farther away from points that are in that data generating process. Whereas on the other side, it's like that's where you're kind of consistently getting things one-sidedly wrong. So the components of the bias portion will actually shrink to 0 when you have a very complicated model, because you're like preventing you're essentially reducing the error portion with the data that you actually see. And so you're going to get more and more consistent with the bias, reducing the bias error. Does that make sense? Yeah. Okay. So what was the strategy that I had mentioned before to deal with this variance error, or to deal with the idea of like overfitting? Does anyone remember? Or like, how can we assess that something has been overfit? Yeah.
We have training and testing.
Yeah, exactly. So the idea is like, you have some data, let's not train our model on all of the data, let's hold some in reserve maybe, or generate the data in some other way to validate the fact that that it fits really well, or to show that it's actually kind of overfitting, right? And so remember that that the fit with any data that you train on will always get better with more complex data, okay, or more complex models. So I want to show an example of this. Okay, so here you don't actually need to follow along with the code. I'm gonna run a bunch of stuff right now, but I will kind of talk through what I'm doing here. Okay, hang on. Let me make sure this is the right one. Yes, okay, cool. Where's my mouse? Okay, so I'm going to create a set of x's and y's. And this is a slightly different curve than what we're used to seeing. And in fact, I'll go ahead and just plot this so you can see. So I have some data that's kind of in a weird waveform that looks something like this, okay? And what I want to do, what I want to show is I'm going to apply a set of models to fit this data that I just generated. And I'm going to make the models more and more complex. And by complex, really all I'm doing is I'm going to add more variables and increase the number of parameters in the model. And what I'm doing is adding polynomial terms. So I'll have, in the simplest model, it'll be a linear model, y equals beta times x. Then in the next one, it'll have y equals beta times x plus beta 2 times x squared. And then I'll do plus beta 3 x cubed, and then I'll do plus beta 4 x to the 4th power, and so on. And every time you add these extra parameters, the way to think about it is you're allowing your line to become more and more squiggly, okay? And we're gonna see what happens with my model fit as I add more and more of these polynomial terms. So here, I'm going from, actually I should change these notes here. This is going up to x to the 25th. And then I'm just generating a set of inputs that I can use to predict from the model that I'm running. And then I'm going to do some test data as well. Okay. So if I run all of this, this is all like bookkeeping stuff. Yeah, all right. 1 second. Okay, so what are we looking at here? So the red line is the fit through my points. And you can see, yeah, in the top left corner, that's just where I have one parameter, so y equals beta times x, and we have this straight red line that goes through the points. Ignore the blue points for a second, we're just looking at black points. And then the next one over is when I have both x and x squared. So I have two parameters, and then x squared, x cubed, three parameters, and so on. And so what you can see is that as I add in more parameters, I'm giving more degrees of freedom to my model fit to kind of move around. And yeah, we can see that reflected in the kind of like the squiggliness of the red line. So the basic idea is from the top left, we start at the kind of simplest model all the way down to the bottom right, where you have kind of the most complex model. And we can see that the red line will actually start to fit the black points better and better as time goes on. And so with the metrics that we've talked about in terms of assessing the like performance of a model, you will see that the size of the residuals will decrease from top left to bottom right, right? So if I were to look at the mean squared error values, you would see that you have the biggest ones up there and the smallest ones down here. Same with R squared. You'll see that the R squared will consistently improve from there to here. It will always get, your R squared will always get bigger and bigger as you go from top left to bottom right. And so those metrics will not tell us anything about overfitting. And the way that we assess the overfitting part, right, is to think about if I were to include other data points in the data generating function, the true data generation function, how does our fit compare to those data points? And so that actually is what shows up in blue. And what you can see happening is that there's a number here that you see kind of in the middle of the chart. That number is the mean squared error, but it's actually the mean squared error of my fit against the new test points. So instead of saying, oh, black point to my line, how far am I? And then add up all of those errors and square, and then divide by the number of data points. You're doing that instead for the blue points compared to the red line. So you are now doing a mean squared error test for data that you did not calibrate on. And what you will see here is it starts really high. So we have a mean squared error, an out of sample mean squared error test of about 0.5, then 0.467, and it will continue. Well, this one maybe is a little bit jankier, but generally the trend you'll see is that it will go down, and then as you start to overfit more and more, the error term will start to increase again. So here we see like 12, 13, 14, 15, your error is about 0.42, 421, 421, 422, 422, and then it starts growing 462, 462, you know, 486, 0.486. And that trend is a reflection of this thing that we're talking about here. Okay, and so the decrease in the mean squared error, in the out of sample mean squared error, that is the bias term decreasing as I increase my model complexity. And then as that out of sample mean squared error goes up, that is my variance error increasing as the model complexity goes up, right? So this is just kind of like an empirical example of that. So sometimes, you know, it's not gonna always look so perfect because, you know, this is you could have random variation in the data and in your models that will, you know, that trend's not gonna be perfect all the time, but generally speaking, you're gonna see kind of a decrease in error from the decrease in bias and then increase as you start to overfit. In this case, we kind of go down and up a little bit at the beginning, but generally speaking, right, our model is kind of performing the best, yeah, in the middle. Okay. Any questions? Yeah.
So if you were choosing a model, would you, even if like number 3 there has like the lowest error, would you still choose one from the middle because it's more like theoretically sound? Or conceptually valid, I guess?
I mean, in this case, yeah, but I mean, generally speaking, we kind of just pick the lowest out of sample mean squared error. This might be due to random chance, so you might run this a couple times and see where you're consistently getting the lowest out of sample mean squared error. Yeah, I'm realizing maybe this particular one maybe has too much noise to be a good example, so maybe I can improve this example, but yeah, you would actually generally try and do this a couple times, and actually we'll show the ways that I'm going to encourage you guys to do this will try and avoid, or will try and accommodate some of the randomness that you might get from sampling. Yeah, and we'll talk about that next. Any other questions? Okay. So, let's jump back to the notes. So how, I'm gonna maybe try and just formalize what we talked about a little bit. So how do we test the goodness of a model? And this is this idea that we can do out of sample validation. Right, and so the idea is something like we have a training set. This goes into calibrating the model. And then we want to test our model. And this would be using, from a separate place, testing data. And whatever metrics we decide to use here, right? So R squared, standard error, residuals, mean squared error. That's probably the big one. This will let us then go back into calibrating the model. And really what you want to do is think about how well the model holds up when we're predicting, right? So if we take a fit line that goes through some data, we take that same line and go through a new set of data, how well does the model essentially hold up? Okay. So the main way that I kind of suggest we do this type of validation is actually through a specific technique called cross-validation. And the idea is, okay, you have some data, and you would like to calibrate your model to that data. Remember how good the model performs in terms of the data that you give it. It's always going to do best with the most data available. So how can we have kind of a training set of data and a testing set of data while kind of maximizing the idea that we would like to calibrate our model to as much of the data as possible, without having to come up with a separate testing data, which may not always be available, right? And if we want to derive the test data from the training data, we're detracting from our model's ability to use as much data as possible in its calibration. And so cross-validation is actually a cool technique that lets us kind of get around this. So let's talk about what cross-validation is more specifically. This is where we use our data set to artificially make a test set. And the common cross-validation technique that we're going to talk about today is called k-fold cross-validation. So this is a procedure that employs the entirety of your data set iteratively to test the predictive ability of your model. On new data. Okay, so what the heck does that mean? Let's do this kind of step by step. So one, k-fold cross-validation, we need to define k. So this is the parameter that divides your data set into roughly equal parts. Let k equals like 5 or 10. Yeah, this is kind of an arbitrary number. And we'll talk about maybe strategies for specific numbers a little bit later. Okay, so step 2, we want to split the data set, and we randomly divide the data set into k equally sized parts. Okay, what does that mean? So, you have a data set. Let's imagine you guys are the data set. Each one of you is one row of data. And let's say I select k equals 5. So I want to divide you guys randomly into 5 parts. So I'll say, okay, you get K1, you get K2, you get K3, you get K4, you get K5, and then I'll continue assigning each of you guys randomly a number. And so that way I can now identify, okay, here's like group 1 of my data set, group 2 of my data set, group 3 of my data set. So you guys are essentially now split into these different parts. Or I could easily split you into these different parts, right? So imagine what that would look like for like a real data set, right? You have a table, you essentially randomly assign each row an index number according to your K, or that's one way you're doing it. But essentially you're splitting up the data. Okay, and so for each fold, I'm going to set aside one fold, and this will be the test set. Then I will train the model on the remaining data. I will validate the model using the test set. And then I'm going to record the performance metric. Right, whether that be your MSE, AIC, BIC. I know we haven't talked about these, but we will cover them later. So what I'm doing is I'm essentially saying, okay, everyone who's a 1, step aside. The rest of you, I'm going to use you guys as my training data, so I'm going to calibrate a model. Then all the data that I left out of group 1, I'm going to use that group to now calculate what my test mean squared error is, my out of sample mean squared error. Okay, and then I'm going to set that number aside. And then for step 4, we're going to repeat step 3 for each of the K folds. Right, and so now I'm going to say group 1, go back into your data population. Group 2, I'm going to put you guys aside. I'm going to run the model again, and then I'm going to calibrate against group 2 that I've set aside. I'm going to calculate a new test mean squared error, and then I'm going to hold that metric. And I'm going to repeat this for group 3, group 4, and group 5. So how many test mean squared errors do I end up with? What was that?
Okay.
5. Because I do for each group that I leave out, I generate one test mean squared error. Okay, so in this particular example where I say k equals 5. Okay, and so then I can take the average of those test mean squared errors, and that would tell me kind of the average test mean squared error for one particular model. And then I could compare against like totally different models. Okay? Doing this helps to alleviate the problem that we were mentioning before, where if it's an error having to do with artifact of the sampling, I can help wash that out because now I'm doing the sampling several times, right? So yeah, the last step, aggregate performance metric. Across all k-folds. And this, right, and so that's taking the average of my 5 test mean squared errors. So you would have something like our full data, and then I would carve a piece of this out. So training, data, and then my little bit of test data. And then I would repeat this k times. There's a form of cross-validation called leave one out cross-validation, which is a special case of k-fold where k is equal to your number of data points. And you can do this for smaller data sets. But generally speaking, k at 5 to 10 is generally a pretty reasonable number of folds to do for this cross-validation. Okay, any questions about this? So this will be a pretty important concept. We're going to apply this kind of throughout the class. This idea of doing cross-validation is not model dependent, right? I could do this for a linear model, I could do this for a logistic model, I could do this for any, a machine learning model. This idea is kind of agnostic to the actual model type. And in fact, a lot of calibrations are going to depend on doing things like cross-validations in some way. And so all of this idea about this bias variance trade-off, right? We are talking about ultimately one of the most prolific strategies to identify in that bias variance trade-off the low part of that error. This cross-validation is the way where we can identify that lowest part of your total error. Okay? Any questions? Okay. So one last thing about this, right? The whole idea is we are thinking about different models. Models that are more complex compared to models that are less complex. That k-fold validation procedure tells us the test mean squared error, the out-of-sample mean squared error of one particular model. But that in itself, it's not like an R-squared where it's a index value. That has to be compared to test MSEs of other models to determine which model is better, right? So the out of sample mean squared error isn't going to tell you anything on its own. It's a comparison metric between models to tell you which one is going to give you more, which one is going to give you the best prediction outcomes, okay? So we are going to now look at, okay, actually I'm going to delete this. Implementing this manually, I think that's the best way to really kind of learn this. So we're going to implement this manually to see in our wages example if one model performs better than the other in predicting earning outcomes out of sample, right? And that's, I think at the end of the day, a lot of, on the predictive end of the spectrum for what we want our models to do, we generate a model to understand relationships between data, and at the end of the day, you really want it to be able to say something about how well I predict my outcome variable. And not only that, how well I predict my outcome variable with data that I didn't calibrate on. So here's two models. Let's say we have a model using height, gender, race, and education, and we want to see if that does better or worse than a model that does age, sex, race, and education. And we want to do this using this framework that I just talked about, which is this like k-fold cross-validation. So let's implement it. And I'm going to write a function, and you guys are going to help me write this function. This input here, I'm just leaving this generically as what I'm going to use as the data going in. What's our first step in doing the k-fold cross-validation? Yeah, define k. So that is an external input. So I'm going to leave that as in one of the parameters, input parameters for the function. We're going to say number of folds. Actually, I will put k because that will be easier to type. But right, k is number of folds. Okay, and that will be externally specified. Okay, step 2. What's step 2? Yeah, so divide the data set into k equally sized parts. Okay, so who can help me here? How do I split my data into k equally sized parts? There's different ways of doing this. Yeah.
I'm thinking of a for loop.
Okay, you could do this in a for. Describe the concept of what you're thinking about in the for loop.
Okay, I was writing while you were giving the example of how you were splitting people in the room. But
Yeah.
my thought was, or what I was able to listen to, was for every, so you divide the data set per se into whatever the k value is, let's say 20.
Okay.
Of each divided group of 20, you grab the first number, and that is group 1 of 20, and then grab group 2 of the 20, and then you keep doing that over and over until you
Okay. And how would you grab the group that you assigned like 1, and then how would you grab the group that you assigned 2?
Okay. Could you
In English, don't worry about thinking about it in code.
could you make every split into a matrix so you have 20 matrices?
Okay, now you lost me. Sorry.
So if you divide everyone in the room, divide them by 20 different groups.
Well, we have k groups. Okay.
Okay. Would you label each group a number number or a string or like a name.
Yeah, okay, so you're saying we make an assignment to every group, right? So I think you're on the right track here. But actually, instead of
More simple.
yeah, well, instead of splitting everyone, you could just assign everyone a random number, right? Between 1 and k.
One index, please.
Yeah, okay. Yes, that's right. So okay, now how would what function would we use to randomly get assignments? Yeah.
I was gonna say sample.
Yeah, sample. And then we'll do 1 to k, right? So it could be an arbitrary k, it could be 5, it could be 10. And so the numbers that I'm grabbing out of the hat are from 1 up to k. And how many times do I grab out of the hat? Huh?
K, like,
Not k.
it's okay.
Number of rows.
Number of rows. Yep, right. So if there's 100 rows, I would want to grab 1 through k 100 times so that I could assign every row one of the numbers from 1 to k. Okay, so this would be n row of input. And do I replace equals true or false? True. Yeah. Okay, so this is my index. And I'm just going to add to my input data, a column called index, which is the index numbers that I just found. So I guess you could just do it like this, input $index, and then skip this row. Yeah. Okay, hopefully everyone's following along so far. I'm just creating an extra column in my input data, and that extra column is just assigning random numbers from 1 through k. Okay, you could have done this in a for loop, although technically a little bit more inefficient computationally wise, but that's not a big deal. But yeah, you certainly could. I think if I were to do this in a loop, it would look something like, for r in 1 to n row input, I would append, I would create a column, and for each one, I would pick randomly from 1 to k, like this. And this operation does the same thing as row 116. Okay? So yeah, you certainly could have done it this way. Yeah?
I have a potentially dumb question. What is this function supposed to return?
We'll see in a second. Yeah. Well, actually, no. You tell me. What should this function return?
I mean, if you put inside the actual formula itself, you could make the function return literally everything, but...
Yeah, but what do we want out of this function based on what I was defining as the steps for getting performing our k-fold cross-validation? Yeah, the out of string mean squared error, and so that is what we'll return, but that'll come later. Okay. So we've done steps 1 and 2. What is step 3? Yeah, well, so more specifically, I'm going to perform a procedure for every fold. And so, in fact, okay. So if I jump over here, right, for each fold, implying that there's a for loop, right? So that I'm gonna have to do this process for each one. So for n in 1 to k, I have to do something. But yeah, so the first thing would be to define the test set. And how would I do that? We now have an index that indicates which group you belong to. Yeah.
Create a variable called, I don't know, data.test.
Sure. I'm going to call it testing.data.
Okay.
That's what I have in my notes. You were really close.
And then filter the inputs.
Okay.
where Index equals
Yeah.
n.
Oh, sorry, I didn't hear you. N equal. Yep, perfect. Great. Right? Does everyone see what's happening here? I'm creating a test set, and that test set is everything in my original data where the index value that I assigned to it is equal to the portion of our for loop that we're in. So on the first one, it'll be 1. In the next iteration, it'll be 2 and 3 and so on, all the way up to k. Okay, yeah.
Can you briefly explain again the difference between 1 equal sign and 2 equal sign?
Yes. 1 equal sign is an assignment. 2 equal sign is to test whether or not the values are equal to each other. Yeah. Yes.
Oh, no.
No, okay, you're just stretching. Got it. What about the training data? Yes, go ahead.
Training.data input is not equal to.
Yeah, that's everything else. So not equal to is exclam equals. That's kind of like strike through equals. Great. So now I have training data and I have testing data. What am I doing with this? Someone else help me out here. Was that?
Like trying to run a model?
Yes, we're going to run the model. Okay, and our first model is height, sex, race, education. So I'm going to create a variable called model hold, which is the thing that's just going to hold all of our model results. And it's going to be LM earnings on height, sex, race, education. Data is equal to, what do you guys think I put here? We're going to run a model. Yeah, sorry. So wages is the input, but remember the whole point of doing this is that we are run the model. Do we run the model on the entire data set? No. What part of the model do we run on? The training data. Perfect. All right. So training.data, right? So training data is the wages data, excluding the portions of it that were assigned k equals 1 in the first loop. Okay. And then I want to calculate my mean squared error. So I'll help you guys out here. So predict here, model.hold. Okay, so I want to generate, the y hat for what set of values? Is it for the original set or for a different set? So mean squared error, y hat minus y squared, but we want to do the out of sample. So if we want to do the out of sample mean squared error, then our predictions should be on the testing data. Perfect. So it's going to be new data equals testing data. Okay, and so now I can calculate the mean squared error, which is the average of testing data earn, which is the right, that's our y, or our output variable, minus the predictions squared. So this is going to give us our test. In fact, maybe I'll just write it as out of sample. Let's be consistent. Out of sample MSE. Okay, I'm going to do the little trick. I don't remember, or I don't know if you guys remember, but we can create a little container to hold our MSEs when we go through a loop. So I'm going to start with an empty container called mse.all, and I'm going to, every time I run through the loop, append into it out of sample MSE. And then we're going to return MSE all. Whew, okay. That was a lot, right? But recap our for loop. We've indexed the data into k different portions, and then we run through the for loop for each portion. We take it out, run the model against the training data, then we take that testing data that we left out, we calculate the mean squared error, that's line 123, and then I'm just going to hold on to that. And I'm going to repeat that k times for the number of folds, and then I'm going to return all of our out of sample mean squared errors. Okay? So I can run this guy. I'm going to now straight up copy and paste this whole thing, and I'm going to make a new function called CV2, and all I'm going to change is the model, right? Because we were testing two models, and we want to see which one does better at out of sample predictions. So on the second one, we change height to age. So all I do is in here, this line 135, I just changed height to age, and I'm calling this a different function, which is kfold.cv2. So if I run this model, let's do k equals 5. Oh, okay, I need to put the input data first, wages. And then let's do k equals 5. And we will compare this against kfold CV2, wages, k equals 5. Okay, so here are the 5 test values, and actually I probably want the average of these to help wash out any sampling variability, and compare that against the average of the 5 test squared errors in the other model. So here and here. Okay. And so this is what I was meaning when I was saying the test squared error really is only relevant to compare against other similar models where you're looking against the same output. So in this case, our test squared error is lower in the second model compared to the first model, which means what? So who's going to help me interpret this? Which one's better, the lower one or the higher one? The lower one, right? Because you have a lower error, like squared error. So the average size of your errors are smaller in the second model compared to the first model. And so thinking about what it means to have a test MSE, what I would say from these results is that on average, we would expect the ability of our second model that uses age as a predictive variable compared to height, that will give us lower prediction errors than our first model. All right? Any questions about this? Yeah.
So, can you go back to where CV2 was defined?
Sure. Right here.
And then one up again for CV1.
It's exactly the same except for this.
Yeah.
Yep.
So that just means height just isn't correlated with.
No, so careful. It's not saying that height is wrong in any way necessarily. All it's saying is that Model 2 will give better predictions than Model 1. Height could have some explanatory power, but maybe not as good as as age, right? Yes.
Could you explain again why that number is so high?
Yeah. So you say it's so high, but it's all relative, right?
Yeah.
Like there are other models that could be much larger, right? So the size of these errors is simply the average of the square error term. We are talking about wages that are in the tens to hundreds of thousands. So if you're off by a couple $1,000s, you square that, your MSE values are going to be in the millions, right? I guess like 1,000 squared is in the millions. So it's all context specific, right? Like if I were to run this exact model where I just scale down the incomes, let's say, instead of reporting in dollars, I reported in thousands of dollars. So in other words, if the earnings were like 79.571, 96.396 or whatever, where you just divide everything by 1,000, well, all of these error terms would be like 1,000,000 times smaller, right? So it's all relative. The things that you are comparing test MSEs to are other models that are running against the same output data. So your Ys have to be the same. You can't just take a wages model and compare it to, I don't know, a disease model and be like, oh, the disease model is better because it has a better MSE. They're not comparable, right? This is not a indexed value like an R squared. It's all context dependent to your data. So it's all about this question of like, oh, I have a bunch of possible different models that I can use against this data set. Which one of them gives me the best predictions? This cross-fold validation is a very powerful tool that we are basically going to use for the rest of class. And I mean, this thing that I just walked us through, again, that's to try and get you guys really comfortable with exactly what's happening in the cross-validation. Obviously in R, someone's built a package to like do this for you, and we're gonna use stuff like that throughout the class, but it's really important for you guys to have a good conceptual grasp of what the cross-validation is doing, and you'll see that show up in the homeworks as well. But yeah, know that in practice, there will be little helper functions that will like do all of this for you. Yeah.
If you run it again, would you expect the same results?
Yeah, let's take a look. So, no, you wouldn't. And that's because of the sampling, right? You are sampling slightly different data points. And so your error terms may go up and down depending just on the artifact of having sampled different data. Now, you could statistically be able to say something with more confidence about how frequently the second model would perform compared to the first one if you were to do this many times, right? And so if I were to do this sampling many times and compare the test errors, and I always got better with 2 than 1, I could be like, oh, I'm like very statistically confident in saying model 2 will consistently predict better than model 1. Okay, any other questions? Okay, so that's gonna be it for today in terms of this material. The homeworks are due the end of the day today. And I am getting kind of occasional questions about this still. Remember that the submissions are required, the 2 pieces of the submission are the R Markdown file and then the compiled file. Okay, and so make sure that you're submitting the right stuff. I'll maybe do like a quick, because I didn't go through this in our tutorial. There is a template file available on Canvas for your homeworks, and so you feel free to use this. And if you haven't done this already, I would highly recommend that you try and do the R Markdown stuff sooner rather than later, because that's kind of the most common area that folks get stuck up on. There are tutorial resources available online that kind of help walk through this, but I'll just do like a quick and dirty version right now. So instead of having to like do stuff in R and then write up stuff in Word and then figure out ways to like merge them, R Markdown is a way to combine kind of the word processing part of it with the code embedded in like one thing. So you can see when I knit this file, this template file, it will include portions that are just like kind of the text word processor thing or part of it, and then you can have code that is highlighted in here as well, right? And so all the stuff in R Markdown is actually able to run the code. So all of the R code can be just embedded into your R Markdown file. Here, you can have code that is explicitly shown in the compiled document, and you can have code that is hidden. So you can see in the compiled document, I have the X arrow 3 and Y arrow 2, right? That shows up here, but then Z arrow 4 does not. And you can use this option R equals true or false to denote whether or not you want to show specific portions of code that's run in your homework. Okay? Yes.
Should we show everything then?
I mean, up to you. Like yeah, I guess generally you can show everything, right? Yeah. There might be something that like isn't necessary to show, but I guess it's safer if you just want to include it all. Yeah, and then the text part of it is just anything like in the normal part of the R Markdown file, and then the code snippets are using the, I don't know what this symbol is, right? Under the tilde, triple apostrophe to indicate that you're in a code portion. Okay? And you can submit either the PDF or the HTML. You're fine with either, right? Yeah. The PDF will look, it uses like a LaTeX compiler, and so it'll look a little bit different from the HTML. Okay. Yeah, so it'll look something like this, as opposed to like this. But either of these versions are fine to submit. Yeah, I've heard that the PDF ones can be a little bit more troublesome for people when they're compiling. So if you're having problems, then generally HTML will be a little bit easier. Okay? Any questions? Yeah.
The instructions said to stick this all in a project file and then zip it up and submit that as well. Do you still want us to do that, or do you just want to submit the markdown file and the native file?
Up to you. You want 2 files or a zipped file?
I think 2 files.
2 files? Yeah. Do it with the 2 files then.
So no project file.
Yeah, I don't think that's necessary.
Unless you have like extra script that needs to be connected to the RMD file, then you submit the whole thing.
Yeah. Okay. Any other questions? All right, then we can end just a little bit early today. Thanks, everyone.